Okay, the next topic is on sequences and series. Okay, and a sequence is just an ordered list of numbers. A series would, and this is informal. We'll define them better later. A series would be a sum of the terms in a sequence. Okay, that's basically what the two things are, right? And the where this topic goes is we have things called infinite series. Okay, so where we have sequences with infinite number of terms in them, and then we have a series that is the sum, the infinite sum of those terms. And so we want to answer questions about those things like, can you add up that infinite number of terms and do you get a finite result? Okay, we said that it's a convergent series. And if so, what is that result? All right. And then those infinite series can be used, certain types of them anyway, can be used to do uh, things like you can represent certain types of functions um, using an infinite series. Okay. Um, and and things like that. So that's the next place that Calc 2 goes to. Okay. So we start with talking about applications of integrals and different techniques of doing integration, and then we talk about some uh, fundamental problems like lengths of curves and area problems and how and using polar and parametric coordinates, right? And those are all really applications of integration. And now we're going to get into what seems like a total change, and it kind of is. It is somewhat different, but at the end of the day, it's really just algebra. Okay, so let's start. Sequence is an ordered list of numbers, right? So we might have, for example, a sequence like 1, 4, 7, 10, 13, and so it goes on forever. And you can see that you get the next number. So we can represent this using a recursive relationship where the n plus first term in the sequence is the nth term plus 3. Okay. All right. And that's how we're going to start. That's how we're going to represent these things, where we're going to represent sequences using shorthand notation like this, where a n plus 1 equals a n plus 3, and this goes from n equals right, say 0 to 0 to infinity, say. All right, so that's just some short, and we'll get into the notation more. That kind of gives you the idea of how you might represent these things. Okay, so the a sub n's then are called the so we're focusing on sequences here, right? The a sub n are the terms in the sequence. So more formally, then, we say that we have a sequence is an ordered list of numbers of the form A1, A2, A3. So it's this ordered list. It can be generated by a recurrence relation that tells you how to generate the n plus first term by some expression some function of the nth term. Okay, and we're usually given the first term. And once you have the first term in the recurrence relation, you can generate all the rests. Okay, a sequence may also be defined with an explicit formula of the form the nth term is some function of n. So that tells you, given n, how to generate all the terms of the sequence. Okay, so either a recurrence relation, okay, where I know the nth term and I know how to generate the next one, or an explicit formula that tells me for any n what the nth term looks like. Okay. So let's look at a couple of examples. The first one will be the example where the nth term of the sequence is given by 1 over 2 to the n. Okay, so the first term would be 1 over 2 to the first. That would be 1/2. The second term, 1 over 2 squared. That would be 1/4. The third is 1/8, and so on as you increase n. Okay, let's look at another here where we have and sequences like functions, right? Sequences can be, can be strictly decreasing sequences, strictly increasing sequences, or ones that are neither of those. And this is an example of one that's neither, where the nth term of my sequence is -1 to the n times n over n squared plus 1. And so you can see with the -1 to the n that this is going to bounce back and forth between positive and negative. So the first one, -1 to the first times 1 over 1 plus 1, so that's -1/2. And then plug in n equals 2. That's going to give us a positive. That's going to be up here. N equals 3 is negative. And you can kind of see that this bounces back and forth, positive to negative. But, as n grows larger, the magnitude of the terms get smaller and smaller. Okay, so give you a couple examples of what of how to generate some sequences. Now, in both cases, in both of our examples, okay, we can see as we increase n, we seem to be heading somewhere, right? In this case, the terms are strictly decreasing, but and they get smaller and smaller as n gets larger and larger. In this one, okay, we bounce between positive and negative. On one side, we decrease, on the other side, we are increasing. But the magnitude of the terms shrinks as n gets larger, and we appear to be headed towards some value, right? The magnitude shrinks, so we're going, it looks like, to 0. So both of those are answering the question of what the limit of a sequence is. If the terms of a sequence a sub n approach a unique number L as n increases, okay, that means can make, and just like any limit, I can make the nth term arbitrarily close to L by taking n sufficiently large. Then we say that the limit as n goes to infinity of a sub n equals L of the sequence exists, right? The sequence converges to the limit L. If the sequence does not approach a single number as n increases, okay, that means either the terms of the sequence go off to positive or negative infinity, or they go towards 2 or more values. They don't approach a single unique value. Just like with any limit, we say then that the limit does not exist. And so we would say the sequence diverges. Okay. So with sequences, there is one fundamental question we have: does the sequence converge? If it does, what does it converge to? Or does it not converge, in which case it diverges? So let's then look at a few examples here. The first one would be the sequence -1 to the n over n squared plus 1. And as we could generate the successive terms, right, the first one is going to be -1 over 2, so -1/2. The next one is going to be positive 1 over, so that would be 5, positive 1/5. And so we see then, as we plot the terms of the sequence, that they keep alternating, but they decrease, and they both appear from both sides to be headed towards a value of 0. So this sequence appears to converge. Okay. Now let's look at another one. Okay, where as you take n off to infinity, right? So you're going to go pi, 2 pi, 3 pi, and so on. Well, the cosine of an integer times pi is going to bounce between -1 and 1. And so in this case, there is no limit because it's not a unique number. Okay, so this is a divergent, even though it doesn't explode to infinity, it's divergent because it bounces back and forth between 1 and -1. Okay, now here's one, -2 times a to the n. Okay, where this is, we start with 1, and so -2 times 1. Okay, where a sub 1 is 1, so that's our first. Then -2 times 1 is -2, and then we go to +4, and then so on. Well, you can see here that the magnitude of the terms increases as a sub n increases, and so this would be a sequence that is also divergent because it heads off to both negative and positive infinity. Okay, the next is going to be the kind of a bad place for it. Sorry, with the light. So let's say a to the n is 4n cubed over n cubed plus 1. So in this next example, okay, we've got a sequence where we have an explicit formula, and generally the formula is going to tell you what values of n, right? So it's going to say n equals 1, 2, 3, and so we know that's natural numbers. On occasion, you'll have sequences defined for integers. So where you have n equals, -1, -2, or maybe for all integers. And so it's, usually there'll be an explicit or a formula to indicate what values of n sequences defined. So in this case, we have a sequence given by this explicit formula, 4n cubed over n cubed plus 1. And so we can generate, say, the first 14 terms of this. And you can see, right, we've got the first is 2, and then 3.556, 3.857, and so on, where the successive terms appear to increase, but that the magnitude of that increase decreases. And appears to approach a value of 4. Okay, so if we keep plotting out increasing values, you'll see that the sequence appears to get ever closer, but not quite making it to 4. And so we would conclude that the limit of this sequence is 4. Okay, the next thing we want to talk about is we want to talk about series. Okay, and you can view series as simply the sum of terms in a sequence. An infinite series then is an infinite sum, right? A sum of an infinite number of terms. And so we want to do first is answer the question, how would it be possible? How is it possible to sum an infinite set of numbers and produce a finite number? Well, look, we're going to use an example that will help us kind of depict this. And so let's consider the following example where um, we're going to take a unit square. So that's a square where all the sides are 1, and we're going to divide it as shown. Okay, so the S sub first, the first division, we're going to divide that in half. And so the sum, S sub n, represents the area of the colored region in the nth figure of the progression. So the first term in the progression, S sub 1 is 1/2. The second term in the progression, it's 1/2 plus 1/4. Okay. And then the third term, now it's going to be 1/2 plus 1/4 plus 1/8, and so on. And so what we have is so the fourth term, 1/2 plus 1/4 plus 1/8 plus 1/16. And you can see that as we increase, right, our sums, we can generate an infinite number of terms, but each one gets quickly gets smaller. The nth term in our sum then is 1/2 plus 1/4 all the way to 1/2 to the n. Okay. And so we can see that the magnitude of the terms in the sequence are going to 0, and the sum is bounded by, it's not ever going to get outside that square, right? And so that means we know that we're bounded, at least on an upper limit, we're bounded by 1. That's the largest area. The whole square is an area of 1, and we're never going to get outside that square. And so you can see that this series is bounded by 1. So it would converge to a finite value. Okay. So let's look at the notation. You can kind of see that here, right? And we're going to introduce, okay, so this is an example of an infinite series. Okay. These values in the series S sub 1, S2, S3, S4, okay, those are called partial sums. Okay. The partial sum is simply the sum of a finite number of terms in the series. So S sub 4 is the sum of the first 4 terms of the series. S5 would be the first 5 terms. Sn is the nth partial sum, the sum of the first n terms. Okay. We can introduce some notation to help us represent this a little more concisely. And the notation here is very important. So we notice we've got the an infinite series. We're going to define it formally as a sequence. We have given a sequence A1, A2, A3. The sum of its terms, A1 plus A2 plus A3 off to infinity, is called an infinite series. And notice the notation. Okay, this is the Greek letter sigma, which is the Greek letter S, and so that represents sums. And you've seen sigma before, I think, when you defined your Riemann integral, say. But this is telling us k equals 1 to infinity, so we're going to add up an infinite number of terms, and k here is called the index. Okay, and so if we have a formula for the sequence that tells us how to generate the nth term of the sequence, then we can use that formula in here for a sub k. So this is an infinite series. The sequence of partial sums S sub n associated with this has the terms. The first partial sum is A1, the second is A1 plus A2, and so on until we get the nth partial term, A1 plus A2, all the way to A sub n. And you can see how we represent that. Okay. If the sequence of partial sums have the limit L, the infinite series converges to that limit. And we write the limit as n goes to infinity of S sub n, that's the partial sum k equals 1 to n of a sub k, equals L. Okay, if the sequence of partial sums diverges, the infinite series also diverges. Okay, so sequence of partial sums is just, you know, the first term, first plus second, and so on. And so we can look at the limit of an infinite series as the limit of that sequence that we already defined, limit of the sequence. So we know how to find that. Okay, so that is infinite series. Let's look at an example here. S sub n is given by n over n plus 1. And so if we generate successive terms in this, okay, the first one is going to be 1/2, and then 2/3, and so on. Okay, as we generate different pieces of the partial sum, we see that we get to, or approaching 1, but don't ever quite get there. Okay. All right. So quick wrap up. That's our overview. We'll dive more into the different topics as we go here, but the sequences or series, okay, how are they similar to functions? We'll both have an independent variable. For functions, it's f. For the sequences or series, it's n. The dependent variable in sequences or series are the terms, the a sub n. For a function, right, it's y equals f of x. The domain of sequences and series are going to be integers as opposed to real numbers. Okay, so they're defined for n equals 1, 2, 3. They're not defined for all real numbers, just the integers or very often the natural numbers. And so we're looking for sums when it comes to sequences or series as opposed to integrals. We're looking at accumulation over a finite interval is a partial sum. Accumulation over an infinite interval is a infinite series. On the function side, right, we're looking for the area, which we find by an integral, or we're looking for the improper integral, which we will talk about later. Okay, that's it, and that's your overview, and we'll get to more detailed stuff in a future video.